Okay, so a sequence is simply a list of numbers. For example, 2, 4, 6, 8 is a sequence. The notation n sub a represents the nth term or the general term of the sequence. The entire sequence is represented by that a sub n notation in set brackets, because we know a set is simply a list of numbers. So if we take that a sub n and we put it in set brackets, we're just saying, hey, we're going to have that set of whatever those numbers are. An infinite sequence, a sub n, is a function whose domain is the set of positive integers. The function values or terms of the sequence are represented by a1, a2, a3, and so on. So a sub n kind of just lives in the middle. It's just, oh, the nth term. We're being generic. We're being general about it. A sequence whose domain consists only of the first n positive integers and not all the positive integers is a finite sequence. So a finite sequence has a finite number of terms, and an infinite sequence has an infinite number of terms. Note that sequences are usually named with the letter A, but any lowercase letter can be used. So let's find the first 4 terms of the sequence where a sub n is defined to be equal to 4n plus 1. Don't make this hard. So a sub 1. Notice that instead of there being an n right here, there's a 1 right here. So all I'm going to do on the other side is where there was an n, replace it with a 1, and then clean it up. We get a sub 1 to be equal to 3. And then for a sub 2, we're plugging in 2 for n. For a sub 3, we're plugging in 3 for n. And a sub 4, we're plugging 4 in for n. And that's it. Those are our first n terms. Questions at all?
Did you mean 15 and not 5?
Oh, yeah, thanks. Anybody else? All right, let's do the next one. We're finding the first 4 terms again, this time for b sub n equal to -1 to the nth times n squared. B to the first, that's going to be -1 to the first times 1 squared, which is -1. B sub 2, that's -1 squared times 2 squared. So that'll be a +4. B sub 3, that's -1 to the third times 3 squared, -9, and b sub 4, -1 to the fourth times 4 squared, +16. You'll notice in this sequence that our answers alternated between positive and negative. That -1 to the nth power, that's what does the alternating of the sign for us. And we use that trick a lot when we want to alternate our terms in between positive and negative numbers. Questions at all? All right, so the next thing I want to do is I want to compare the graphs of f of x equals 1 over x and a sub n equals 1 over n. F of x equals 1 over x is a graph that we're familiar with. It's all these points, and then we connect the points with our solid red line, and we know that when we have a solid line like this in a graph, that means that there's a point every single spot along our graph. If I want to graph a sub n equals 1 over n, I'll start by getting a first few terms. N has to start at 1. because the domain is a set of positive integers. So a sub 1 is going to be 1, a sub 2 a half, a sub 3 a third, a sub 4 a fourth, a sub 5 a fifth. So if I plot these points, we get this right here. But the big difference is I don't connect the points. You see, it's just going to be those 5 points. Now, of course, they would extend infinitely as n got larger. It would keep going, but we don't actually connect any of the points. A sequence is a function whose domain is a set of positive integers. If I connected these points, then I'd be saying that I had a point with an x value right here of 1.5 or 2.1 or 3.8, and those aren't positive integers. So the graph is only going to consist of those red points. It's a set of discrete points, which just means like different points that are real numbers. Any questions on that? Do we see the difference between the two? Well, so far, the formulas used for the nth term of the sequence express the term as a function of n, which was the number of the term. Like for a sub 2, we plug 2 in for m. Sequences can also be defined by something called a recursion formula. A recursion formula defines the nth term of a sequence as a function of the previous term. So this is what a recursion formula would look like. A sub n equals 5 times a sub n minus 1 minus 3. They have to give us the initial term. So a sub 1 equals 2, and n is going to be greater than or equal to 2. So this right here, this a sub n minus 1, that's what tells us the previous term. See, because if we're trying to find a sub n, the one before n is going to be n minus 1, so a sub n minus 1 is our notation. If I want to find the first 4 terms, well, they've told us that the first one, a sub 1, is equal to 2. To find a sub 2, my recursion formula here says, well, take the previous term. I'm trying to find a sub 2, so the previous term is a sub 1. Take the previous term, multiply it by 5, and subtract 3. And we get 7. So then to find a sub 3, I'm going to take 5 times the previous term, which was 7, and subtract 3. We get 32. To find a sub 4, we're going to do 5 times the previous term, which is 32, minus 3. I don't know what that is. 157, does that sound right? And those are our first 4 terms. Questions on how to write out the terms when you're given a recursion formula? Okay, next up is factorial notation. You may have seen this in high school. You may have never seen it before. Products of consecutive positive integers occur quite often in sequences. These products can be expressed using special notation. So if n is a positive integer, the notation n with an explanation. So n with our exclamation point is read n factorial. It's the product of all positive integers from n down through 1. So n factorial is n times n minus 1 times n minus 2 times n minus 3, all the way down 3, 2, 1. Also note that 0 factorial is equal to 1. So I just want to throw out here, so yeah, we use the exclamation point for factorial, but it also can mean the word unique. So I just want to tell you that because in another context, you might be like, hey, isn't that supposed to be factorial? But sometimes we use the exclamation point just to mean the word unique. Not in this, that's not what we're going to be doing in this class at all, but I just want to throw that out there. All right, so let's evaluate 10 factorial divided by 8 factorial times 2 factorial. Now, so 10 factorial means 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And on the bottom, we have 8 factorial. So that's 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. And then the 2 factorial, that's just going to be 2 times 1. Now, it would be ridiculous for us to figure out what that number is on in the numerator and what the number is on the denominator and then try to simplify the fraction. That would just be ridiculous. So what we can do now that we have it in our expanded form is we can start canceling factors that are on both the numerator and the denominator. So we're going to be left with 10 times 9 over, that should be 2 times 1 here on the bottom, over 2 times 1, 90 over 2. This simplifies to be 45. I want to point something out here. Notice that when we wrote out that 10 factorial, it's, 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. But 8, 7, 6, 5, 4, 3, 2, 1 is 8 factorial. So once you get comfortable with the notation, like I wouldn't have written out all of that. What I would have done is I would have said that 10 factorial is 9 times, that's not right. It's 10 times 9 times 8 factorial. And then I would have left 8 factorial on the in the denominator and then canceled the 8 factorial. So once you get comfortable with the notation, I would encourage you to try to do it that way so that you're not having to write them all out, because I mean, what if the number's 512 factorial over 517 factorial? You don't want to have to write out all those numbers. That's crazy. All right, so let's look at it kind of in a generic form. N factorial divided by n minus 1 factorial. Well, n factorial ends up being n times n minus 1 times n minus 2 times n minus 3 times n minus 4 and so on. So it becomes n times n minus 1 factorial. And then we're over n minus 1 factorial. These are going to cancel and we're left with just n. When we're in this generic sense, we kind of have to do it that way, because how would you know how many to list out if we tried to list all of them out? Questions at all? All right, so one more. Here we have 5 factorial minus 4 factorial. When you have an operation of addition or subtraction, you have to write out the expanded form and just figure out what the numbers are and then subtract them. We didn't have to do that here because we're like canceling common factors because we're dividing, but when it's addition or subtraction, you just got to figure out the numbers and do the operation. So 5 factorial, 5 times 4 times 3 times 2 times 1, we get 120. 4 factorial, 4 times 3 times 2 times 1. So 5 factorial minus 4 factorial is going to be 120 minus 24. We get 96. Questions, anybody? All right, well then why don't you guys find the first 4 terms of this sequence that has a factorial in the denominator. I'm not going to break into groups because it should just take you a minute. So just give you a couple minutes to do this. All right, so these are what I got for my first 4 terms of the sequence. Anybody get anything different? Have any questions?
For the fourth one, it should be 1/6, I believe.
Say that again.
For the fourth one, shouldn't it
Oh
be
yeah,
like
sure
1/6?
enough. Sure enough. Yeah. Canceled a 10, so I wrote 10. Anybody questions at all? All right. Sometimes it can be useful to find the sum of the first n terms of a sequence. The sum of a sequence is called a series. I don't know why. When I was a student, I could not remember the difference between a sequence and a series. So I finally have like a way to help me remember it, that the word sequence has more letters to it. It's like long, and series has less letters to it. So the sequence is the long list of numbers, while the series is the short sum of the numbers. So that's what helps me remember. So if we have the finite sequence 1, 4, 9, 16, then the series is going to be 1 plus 4 plus 9 plus 16, which equals 30. So the sequence is the list of numbers. The series is 30. It's the sum. There's a compact notation for expressing the sum of the first n terms of a sequence. And this is called summation notation. You're going to use this a lot. You're going to use this a lot in Calc 2. That I still remember to this day exactly where I was doing summation notation for Taylor series in Calc 2. Remember that very vividly. So this is something that we need to be comfortable with. So first we're starting with this weird looking E. It's actually the capital Greek letter sigma. So sometimes you'll hear them say sigma notation even. Summation notation is really the better term. So what we do is we write our big sigma. On the bottom, the whatever letter is on the bottom, I is most common, but J, K also super common. I is the index of the summation. It tells us where to start. So it's going to say start at I equals 1. 1 is our lower limit, so it tells us to start by plugging 1 in for I. You know, kind of like with our a sub n, where are we starting? Well, I'm starting at a sub 1. And then the n on the top, well, this is our upper limit. This tells us where to stop. So if this is a finite sequence and we want to add up the first 10 terms, we're going to see the sum from I equals 1 to 10. It tells us add up the first 10 terms. Then whatever's here where this a sub I is, that's going to be our formula. Like up here when we were writing out the first 4 terms, it gave us a formula here. That's what we're going to see, something like 4n minus 1. And that notation just tells us to list out the first whatever 10 terms and then add them up. Please note that our lower limit can be a number other than 1. Maybe it wants us to add numbers, 10 through 15 or something in our sequence. When we write out the sum that's given, so it's given in summation notation, but we write out the long list of numbers to be added up, that's called expanding the summation notation. And most of the time you're finding a sum, that's what you have to do. You just have to write out the list of numbers and add them up. There'll be some that we have specific formulas for, but not many. So we want to evaluate the sum from I equals 1 to 4 of 2i. So it's telling us to start at I equals 1 and stop at I equals 4. So I'm just going to plug in, list out those numbers, and then add them up. So this is going to be 2 to the first plus 2 squared plus 2 to the third plus 2 to the fourth. And I want to add those numbers up. So it's going to be 2 plus 4 plus 8 plus 16. This series is equal to 30. Questions at all? All right, let's try another one. This time we want the sum from k equals 4 to 7 of k times k plus 1. So we're going to start with 4 and plug it in for k. And then just go right up the line of integers until we get to 7. I'm sorry, you guys finish that up. I got to get my kid on his Zoom chat. He closed it out. All right, so what'd you guys get for a grand total?
I got 148.
All right. Okay, and then our last one, we want the sum from I equals 1 to 5 of 4. So what's different about this one?
There is nowhere to plug in I.
There's nowhere to plug in an I, right? So this is a constant. So we are going to just add up when all you have is a constant. That means that every single term in the sequence is equal to 4. So we're going to have 4 for I equals 1, I equals 2, I equals 3, I equals 4, and I equals 5. So we're just adding up the constant of 4 5 times. And we get 20. Next, we're going to go the opposite direction. Here, I'm going to give you the expanded form, and I want you to write the summation notation. This is definitely the harder direction, especially when if you get, high up into math. Real analysis, we do a lot with the sequences and summation notation. I was always terrible at finding what the summation notation was with it. So what you really want to do is try to look for a pattern that corresponds with integers, because the domain of our sequences is the set of positive integers. So it can be helpful to write just your set of positive integers, at least for me, underneath, just to see if I can find a pattern. Well, I'm going to start with my sigma notation. I equals, my first number is 1, and then I'm stopping at 9. So that tells me I want to go the sum I equals 1 to 9. And so I said we're looking for a pattern that corresponds with the integers. So our integers 1, 2, 3, all the way up to 9. What's happening to those integers? Well, they're being squared. So I squared is the definition statement to our sum. Questions at all? All right, let's try the next one. So I'm going to start doing the same thing. Oh, geez, this is all the way up to the n-1 term here. So let's start our sigma notation. I'm going to start I equals 1. Where are we going to stop? If we're starting at I equals 1, what's our upper limit? I'm sorry? N, yep. And now we need to figure out our definition over there on the side. We're looking for a pattern between our integer domain values and the numbers that we're actually getting in the sequence. Anybody have any ideas?
I to n-1.
Say that again for me.
I to the n-1.
I to the n-1. All right, so let's try it. A lot of times what I'll do is I'll write the definition and then I'll plug in some numbers and then see if I get the numbers in the sequence. All right, so if I plug in Well, so the problem with this is I have two variables. So I know I have an issue right out of the gates because I should only have one variable, because if all I'm doing is plugging, integers in for I can't have a second variable of n in there as well.
So I to the minus 1.
Okay, so what do you want it to be instead?
I to minus 1.
So the exponent is always 2 minus 1. So
Mhm.
that might as well just be a 1. Right? If you have 2 minus 1 in the exponent, that just simplifies to be 1. And if we have I to the first, then I should have 1 to the first, 2 to the first, 3 to the first, 4 to the first, and so on. And we see that that does not match up with the numbers we actually have in our sequence. So good idea, not the right one. Let's try something else.
Why can't you use I to the minus 1, negative 1?
Okay, so you want to switch to I to the negative first power?
Yeah.
Okay, so then we're going to have 1 to the negative first, which is just 1, 2 to the negative first, which is a half, 3 to the negative first, which is a third, 4 to the negative first, which is the fourth.
It's getting closer.
We're getting closer, right? So
To get rid of the 3 and 5. And
right, so we want these, and we want like, well, wait, 6 to the negative 1, that doesn't work either.
mhm.
7 to the negative 1, that doesn't work. 8 to the negative 1, that's on our list.
Is there any way it could be 1 over 2i?
Let's try it. 1 over 2i. See if that works. All right, so if it's 1 over 2i, I'm going to put 1 in for the first one, and my very first term is a half. And then the second one would be a fourth, and then a sixth, and then an eighth, and then a tenth. So we're getting a little bit closer. We have less extra numbers, but the problem is we're starting with a half. All right, so I'm letting you guys struggle, but it's actually awesome when the last term has an n in it, because right there, that's your definition. You just got to put an I where the n is. But it's not always going to be that way, and we have to figure it out. So I kind of wanted us to go through the struggle of trying ideas, writing it out. Oh, that doesn't work. How can I change it slightly so that we can see it? Notice that all of the denominators are powers of 2. 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. So I'm going to write this above it. This is 1 over 2 to the 0, 1 over 2 to the first, 1 over 2 squared, 1 over 2 to the third. So we need it to be in the denominator. It's powers of 2, but the exponent is 1 less than our n, so that's why it's n minus 1 there. We're going to have the sum from I equals 1 to n of 1 over 2 to the I minus 1. Questions at all? All right, let's try the next one. So this is more like what we see when we usually have to come up with it ourselves. So we just have a series here, a sum of numbers, and we got to figure out what the pattern is. And I'm trying to relate it to positive integers. So 1 through 6, at least I know that I'm going to have the sum from I equals 1 to 6 here, but now I have to figure out some kind of formula that when I plug in 1 for I get 30. When I plug in 2 for I get 26, and so on. I'm actually going to put you guys in groups for a couple minutes to figure it out. It shouldn't take you long when you're all together, I don't think. So I think I'm just going to put the ADU in 2 groups of 4. See what you come up with.
Yeah. And like looking at all these sequences, it reminds me of recursion codes and such.
Well, we even use the word recursion formula, right?
Yeah.
So very interconnected. We'll do ones that are, moderate level in Calc 2, and the tough ones really come in real analysis, but unless you are a pure math major, you don't have to take that course. All right, so now we're going to look at a specific type of sequence called an arithmetic sequence. An arithmetic sequence is a sequence such that the difference between 2 consecutive terms is constant throughout the sequence. The last one we just did was an arithmetic sequence because you saw it was -4, -4, -4 every time. The constant difference is called the common difference of the sequence. The common difference D is found by subtracting any term from the term that directly follows it. So we want to find the first 5 terms of this arithmetic sequence where the first term, a sub 1, is 300 and our common difference D is 50. So all we do with this when they tell us it's arithmetic and we have this common difference is all we're doing is adding that over and over from the previous term. So a sub 2 is going to be 350, a sub 3, 400, a sub 4, 450, a sub 5, 500. Right? So just every time we're just adding 50. An arithmetic sequence is a linear function whose the domain is the set of positive integers where the common difference serves as the slope. The recursion formula of an arithmetic sequence is a sub n equals a sub n minus 1 plus d. And that's really what we did. We just took the previous term and added that d value over and over again. So here we just want to write the first 5 terms, but it's written out as a recursion formula. Remember, with recursion formulas, they have to give you that first term to get you started. So a sub 1 is equal to -7. Looking at our recursion formula, like definition here, what am I adding every time?
4.
4. So -3, +1, 5, and 9. Questions at all? So I said that some of these types of sequences have formulas. So we're going to have formulas for these type which are arithmetic sequences, and another type that we're going to do next week called geometric sequences. But other than that, we don't have any. We're not going to have any formulas for a long time. The general or nth term of a sequence of an arithmetic sequence with the first term being a sub 1 and the common difference being d is a sub n equals a sub 1 plus n minus 1 times d. So basically you're starting with, here, I want to go back to Jason's because that was perfect, how he wrote it out. right? He wrote exactly this, that he started with the first term, so a sub 1 plus the common difference. Now ours here was -4 because it was getting smaller, and then n minus 1. We were using I, but n minus 1. So that was perfect. You use the n minus 1 because we don't actually want to add the common difference to the first term. We want to add it to every term after that. So right there's our formula for the nth term of an arithmetic sequence. A sub 1 plus d times n minus 1. You'll definitely want to know that, or at least have it ready for quick reference for the final. We want to find a sub 16 when a sub 1 is 9 and d is equal to 2. So it's super nice to have this formula so I don't have to write out 16 terms to figure out what it is. So a sub 16 is going to be 9 plus, I actually like to put the d first, 2 times 9 minus 1. So 9 plus 16, a sub 16 is 25. So why don't you guys try the next one, just on your own. Everybody good with 685? Questions at all? Okay, so now we're going to go the opposite direction. Here, I'm giving you the sequence, and we want to write a formula to represent the nth term. This is super common. We do this all the time. So what we want to do is we want to figure out, well, we need a couple things. We need to know what a sub 1 is, we need to know what n is, and we need to know what d is. Well, actually, we don't need to know what n is. We're just going to leave n in there. So all we need is a sub 1 and d, and then we're going to just plug it into that formula. So our a sub 1 is equal to 6. And then our d value, what's our d value? And that's just what's happening consecutively with our numbers. Anybody ideas? D value?
Going down by 5 each time.
It's going down by 5. So since we're going down by 5, that d value is going to be a -5. So a sub n is going to be equal to our a sub 1 plus d times n minus 1. So that's going to be 6 minus 5 times n minus 1. And that's it.
Also, I want to give a slight correction to the first example. You wrote 9 instead of 16.
I wrote 9 and oh, geez, thank you so much.
The answer is actually 35.
Thank you, thank you. So 39.
35. Oh, wait. No, wait, 39. Yeah.
Okay, there we go. Thank you so much for catching that. All right, let's try this next one. We're writing a formula for the nth term of a sequence, and we don't want to write a recursion formula, but they gave me a recursion formula. So I want to take this recursion formula and make it not a recursion formula. What we need to do is figure out what our a sub 1 is and what our d is, and then we just plug it into our formula. Well, they explicitly tell us that our a sub 1 is 1. What's our d value? Well, with the recursion formula, it says, hey, take the previous term and then add 2 to it. So if we're always adding 2 to our previous term, then that makes our d value equal to that plus 2. And then we plug into our general nth term formula. A sub n is going to be equal to 1 plus 2 times n minus 1. And that's it. Questions, anybody? Sometimes, right, we want to add up these sequences and we want to get a series. We want to add up the first n terms. The sum of the first n terms of an arithmetic sequence, which is denoted by S sub n, so the sum of the first n terms, S sub n, is called the nth partial sum and can be found without having to write out all the terms and add them up. This one actually has a formula. Again, not many of them do, but this one actually does. So the partial sum of the first n terms of an arithmetic sequence is given by S sub n equals n divided by 2 times a sub 1 plus a sub n, in which a sub 1 is the first term and a sub n is the nth term. So I want to show you where this formula comes from and why it makes a bunch of sense. So this is the math history on this. Gauss, famous mathematician, if you remember from matrices, Gauss-Jordan elimination, Gaussian elimination. So I'm talking about Gauss here. He was a math prodigy from the beginning, right? And I'm sure his teachers were just, loved him. I know how I feel about my smart ass kids now and then. So I guess he was young, like 6, 7 years old, and he was being disruptive in class just because he was bored. So his teacher was like, yeah, go over there, you add up the first 100 numbers. You go add up 1 through 100. And he comes back like 90 seconds later with the answer. And the teacher, that was not what she was going for. And he developed, when he was just a child, this formula right here. So let me show you how it works and why it makes sense. So I'm not going to try to add up the first 100 numbers, but I'm going to try to add up the first 10. Okay, I'm just going to add up the first 8 because I'm running out of room here. So what Gauss noticed was, if you took the first number and the last number and added them together, you got 9. If you added the next closer pair in, oh wait, you got 9 again. And 9 and 9. So he noticed that every time, if you took like kind of the outer pairs, they added together to be exactly the same number. And the number of pairs you have is half the number of total numbers that you have. So our formula, if we look at it, the a sub 1 plus n is all those 9s that we're getting. So every time we like work our way in, we're getting that same number as we got when we did a sub 1 plus a sub n, and then the number of pairs we have is half of the total number of numbers. We had 8 numbers, we have 4 pairs. That's where the n divided by 2 comes from. So yeah, this the smart 6-7-year-old kid, when the teacher was trying to give him some kind of punishment, comes up with the formula for the partial sum of the first n terms of an arithmetic sequence.
That's ridiculous.
Isn't it? Right? I'm sure that teacher was pissed.
That's disgusting.
Before they were playing Minecraft, right?
Holy sh-
So we need 3 different things to be able to find the partial sum of an arithmetic sequence. We need the first term, the last term, and then the number of terms. So let's find the sum of the first 50 terms of this sequence here, -15, -9, -3, 3, and so on. Now, again, we need 3 things. We need the first term, we need the last term, which is the 50th term, and then we need to know that, well, n is equal to 50. All right, well, a sub 1, they gave it to us, -15, but they did not give us a sub 50. So we need to figure out a sub 50. How might we find that? Well, we're going to use our formula that says a sub n is equal to a sub 1 plus d times n minus 1. What's our d value? So what's happening to consecutive terms? Plus 6 this time? Or a sub 50 is equal to -15 plus 6 times 50 minus 1. So a sub 50 is 279. And we're going to plug it now into our formula. S sub n is equal to the first term plus the last term times half the number of numbers, because we're pairing it up. And again, I like to give the history on it because I think it helps us remember the formula, because we're adding the first one and the last one, and then the number of pairs we have is half the number of numbers. So we're going to put 50 divided by 2 here, and then we're just going to pop that in our calculator. S sub n, 6,600. Questions? All right, I see it's 10:40. You guys want me to stop here, or you want me to finish these last 3 examples? I don't care, either way. Anybody have an opinion?
Can we just do the these 2 and then do the word problem next class?
Sure.
Yeah.
All right, so let's find the partial sum. I equals 1 to 20 of 6i minus 4. And I think this is what gets tricky too, is because I can change the notation. So these directions and the directions before it mean exactly the same thing. So we have to be comfortable with that notation. I know that this is an arithmetic sequence because I'm adding the same thing over and over again. See, I'm adding 6 over and over again. Remember, it said when it first defined the arithmetic sequence that the common difference was like the slope. So if I rewrote, so if this is like mx plus b, we see 6 is our slope there. All right, well, we need a sub 1, we need a sub 20, and then we need to note that n is equal to 20. So to find a sub 1, we're just going to plug it into our formula right here. So 6 minus 4 is 2. For a sub 20, again, we're plugging 20 in there for I, so that's 120 minus 4, 116. And we're ready to plug it into our partial sum formula. I'm going to take the first term plus the second term. That gives me like my paired up number, and then I'm going to multiply it by half the total number of numbers, because that's how many pairs we have. So S sub n, 1,180. Questions? All right, I'm going to put you in groups to try the last one here. I'll give you a couple minutes to get that done.